In this lesson, we're going to examine one of the aspects that we can actually use counting techniques for in other areas of math. This idea is called the binomial theorem. A binomial we know is a two-term expression, like all the ones you see on the board here. And what we can do is we can take a counting technique, like combinations, and use it to do something algebraically. We're going to get to that in just a second. First, we're going to do some algebra to remind ourselves of how this works. So I want to expand these expressions. In other words, I want to get rid of the brackets. So our first one here, x plus y to the 0. We know the idea of 0 and exponent means anything to the power of 0 comes out to 1. So this is a nice easy one. The whole thing to the power of 0 comes out to 1. The next one, a power of 1. Well, that means just the same thing itself. So we end up with x plus y. The next one, x plus y squared, is where we have to start to think about algebra a little bit. A bracket squared means we have two of them. And then we can do FOIL. X times x is x squared. X times y is xy. Y times x, also xy, or yx. I'm just going to write them in the same order to make life a little bit easier. And y times y is y squared. And if we collect like terms, we end up with this expression. Okay? Hopefully this is so far so good. Let's take a look at the next one, the fourth one here. Just move these out of the way. The fourth one here, I have x plus y cubed, which means x plus y times x plus y times x plus y. Now, we know what this comes out to. We've already done that. It comes out to x squared plus 2xy plus y squared. Well, if I want to multiply that by the third bracket, I can do the idea of FOIL. That is, we're going to multiply everything in the first bracket by everything in the second. So x squared times x will give us x cubed. X squared times y is x squared y. And then we'll do the second one. So 2x times x is 2x squared y and 2xy squared. And then the last one, y squared times x is x y squared, and y squared times y is y cubed. Now if we collect this, we end up with x cubed plus 3x squared y's plus 2xy squareds plus y cubed. And I'm going to pause for a second here and go back to my previous examples for a second. And what I want to do is I want to look at the answers, but more importantly, the coefficients. That is the numbers in front of the letters. So the first one is just 1. The next one is 1x and 1y. The third one was 1x squared, 2xy's, and 1y squareds. So if you notice, so far we have a 1, and then a 1 and a 1, and then a 1, a 2, and a 1. And in our most recent one, we have a 1, a 3. Oh, there's a typo. A 3, and a 1. In other words, we have Pascal's triangle. So if I wanted to do the fifth one here, this x plus y to the power of 4, give you a hint, we can figure out the numbers pretty quickly. The numbers are going to be 1. If I take these two answers, I get 4. And these two, I get 6. These two, I get 4 and 1. I know the numbers right off the bat. I actually also know what the letters are going to be because they also follow a pattern. If you go back and look, we started off with nothing, no letters. Then we had 1x and no y's, and 1y but no x's. And then we look at the next example, we had 2 x's, then 1x, then no x's. No y's, the 1y, 2 y's. So it seems like the x's start at the exponent and go down, and the y's start at 0 and go up. If we look at the third example to confirm, let's take a look. So our exponent was a 3, and we have 3, then 2, then 1, then no x's. And the y's do the opposite, no y's, 1y, 2 y's, 3 y's. So just guessing, this should be x4, y nothing, x3, y1, x2, y2, x1, y3, and no x's, but y4. If you wanted to, you could confirm this, but you'd have to do it the long way. You'd have to do x plus y times x plus y times x plus y times x plus y. My way, this idea of Pascal's triangle and patterning, goes a whole lot faster. Okay, so that's the idea behind the binomial theorem. We're going to try to avoid using FOIL and instead using the idea of patterning and combinations, Pascal's triangle. So here's how it's going to work. When given an expression in this format, okay, so you have a first piece, a second piece, and an exponent, we can expand it. We can get rid of the brackets by using the binomial theorem. That's this formula right here. Okay, the formula means I have to add up. So this is the sum of, we're going to add some things. We're going to add the terms of Pascal's triangle, okay, from row n. N is your exponent. That's how I know which coefficients to use. Times the first term, so the first part, and its exponent is going to go down over time, times the second part, and the exponent is going to go up over time. So this goes from n to 0. This one goes from 0 to n. And if that doesn't make sense yet, don't stress. We're going to go through some examples and just get the hang of this. I just want to point out, in the end, there's always n plus 1 terms. So if your exponent is n, there's always going to be one more term than that. And the reason why is terms start counting at term 0. Okay. One more little trick for you, just to point out, if you're doing this and you do it properly, the exponents are always going to follow a pattern. Okay. In the previous one, we went 3, and then we went 2, and then we went 1, then we went 0. It was not always going to be that kind of pattern. They could actually go up. Okay. They could go by 2s. They could go by halves. Okay, but they're going to follow a pattern. And if your variables are different, like they were in all these questions previously, the sum of them always adds up to n. So if you go back for just a second here, look at these examples. 2 plus 1 makes 3. 1 plus 2 makes 3. 3 and 0 makes 3. They're always 3. In the question, we had a 3. Okay, so let's try one. I want to expand this using the binomial theorem. So this is the next stage. My n is 5, which from Pascal's triangle, okay, I can read it out here real quick if we need it. Hopefully we have a sheet that has that on it nearby. I need to have the 5th row of Pascal's triangle. So I need those numbers. That's the 5th row. I know it's the 5th row because the 5th term, or sorry, the second term is my row number. It's a 5. Okay, so what am I going to write down? Step 1. Step 1, we're going to write down the parts of the problem. So, what do I have? I need a 1 plus a 5 plus a 10 plus a 10 plus a 5. Oops, it's not a 5. Plus a 5 plus a 1. And then what do I need? I need to start off with the first piece, which is x to the power of n. N is my exponent. Times the second piece to the power of 0. So the first one always starts at n, the second one always starts at 0. And then we go down with the first and up with the second. Down with the first, up with the second. And so on. And so on. Oops, that's a 4. No, it's 3, sorry. 3, 2, 1, 3. Down with the first, up with the second, down with the first, up with the second. That's stage 1. Stage 2, I just move this away for just a second. I need that. All right, step 2, we're going to simplify each part. So what does that mean? Well, the number is a number, but I'm going to actually calculate what this is. Now, in this case, it's pretty easy. That's x5. And calculate what this is. That's the number 1. Remember, it's multiplying, so we'll write it that way. So we get that, x to the 4, y to the 1. And some of you are probably thinking, well, this is kind of repetitive. 4, and it is in this case. But that won't always be true. We'll do some examples in a second where it actually gets more complicated. Okay, so we're just doing the exponents on each part. So I got 1 and 1 and, oh, we're out of room here, y 5. All right, stage 3. We're going to multiply the parts together. Okay, now, I did this as a 3-stager. We probably could have done it as 1 just because it's a very simple problem. There's just an x and a y and a number. We probably could have done it quickly. But this process we just did will work on any question. So if we multiply this all together, we end up with 1x5. This all together is 5x4y, 10x3y2, 10x2y3, 5xy4, and 1y5. And there's Pascal's triangle used to expand a binomial. So as I said, that one you could probably do in one line because we know the pattern and it's a very simple problem. But if we look at one like this, which is not so simple, which has the same letter in fact, and it's got more parts and pieces, the process is helpful. So let's try that process. Step 1, I need to figure out the parts of the problem. So I need the 4th row of Pascal's triangle. So my coefficient, my first one is 1. My first part will be the power of 4, and my second part, which is negative x squared, to the power of 0. Okay. My next number from Pascal's triangle is a 4. Now my exponent needs to go down, and the second exponent needs to go up. And then we got a 6. Oops. And then we got another 4. And then we got the 1 at the end here, out of room, so we'll put down here. And there's step 1. The parts of the problem. Your exponent should always add up to 4, because that's what n is. And now we're going to do each part. So 1 is 1. But the next piece, I have to figure out what 2x to the power of 4 is. So I need to think about 2 to the 4, which is 16, and also x to the 4, which is x4. Okay. I need to do all of this to the power of 0. Well, that's the number 1. Next, 4. 2x cubed. So 2 cubed is 8. And this next one here, I could do all that to the power of 1, which just keeps it the same. Next one. 2x squared is 4x squared. This one you got to be careful here. Okay, it's negative 1 squared, which is 1. But it's also x squared squared. A power to a power means we have to multiply those exponents. So we get x4 plus 4. That one's easy. The next one, if we do all this, we'll get a negative 1 cubed, which is negative 1. And x squared cubed is x6. And the last one, we get x8. So there's my simplifying. My third stage is I have to multiply the pieces together. So if I multiply all this together, we end up with 16x4. The next one, I multiply them all together, and be careful here. 4 times 8 times negative 1 will give me a negative 32. Now, these two things have to add. And they add because our rule is my bases are the same, and they're both x's. I add my exponents. So I get x5. Okay, the next set, 24x, add my exponents, and I'll get 6. The next one, it's a minus sign because I have a negative in there to multiply with. 8x7, and the last one, 1x8. So some quick tricks to make sure you're on the right track. N was 4 at the top up here, so I should have 5 terms. And I've got 1, 2, 3, 4, 5. Nice. And my exponents should follow a pattern. And they do. They go up by 1 each time. It didn't start at 0. It doesn't have to start at 0. It depends on the question. Okay, hopefully that one made a little bit more sense. I'm going to try one more. Yeah, really messy looking one. Okay. So what can I do with this? Well, if I go back to some of the exponent rules that we learned in grade 11, we can rewrite this messy looking question as something a little bit easier to work with. We know that a root sign is the same as an exponent of 1/2. We also know that a fraction as an exponent of 1 can be rewritten as a negative exponent. So a better format for this question Same question, just better format as x to the half plus x to the negative 1. And I like it in this format so I don't have to worry about having fractions or root signs. Once I've done that, I'm ready to do the question again. My stages, okay, write out my parts. Need row 3, so 1 times x to the half to the 3, x to the negative 1 to the 0. First one starts at n, second one starts at 0, plus 3, x to the half to the 2, and the 1 to the 1, plus 3, x to the half to the 1, x to the 1 to the 2, plus 1, x to the half to the 0, and around the room again, x to the negative 1 to the 3. Okay, there's your parts. Let's calculate each part separately. So 1 is 1. Now here I got a power to a power, which means I have to multiply these exponents together. So 1/2 times 3. Well, that's, you can use fractions if you want, so 3/2, or if you want to do decimals, that's 1.5. Power of 0 just comes up to 1. 3. 1/2 times 2, well, that's just x to the 1. The negative times the positive, well, that's a negative 1. Plus, half of 1 is 0.5. Negative 1 times 2 is negative 2. And the last one, negative 1 times 3 is negative 3. Okay, there's my parts. Simplified, let's multiply. Altogether, I got x, 1.5, plus 3x. Remember, we have to add these exponents, right? So really, 1 plus negative 1 makes x to the 0. Do the next one, we get 3 again. If I add these two exponents up, I get negative 1.5. Oops, I need an x in there, sorry. X to the negative 1.5. And if I do these together, I end up with, well, just number 1, and x to the negative 3. We start with an exponent of 3 as our n value, so we have 4 terms, check. Our exponents follow a pattern. They're going down by 1.5 each time. Makes sense. Okay, that's how we can expand with the binomial theorem. Try one last example. We're going to try and work backwards this time. Backwards is actually way easier than forwards, because there's some things you can figure out pretty quickly. So I have an expression, big long one here, and I want to rewrite it back in its bracket form. Well, some things I know right off the bat. I know that there's 1, 2, 3, 4, 5, 6 terms. So I know what n is. N has to be the number 5. It's always 1 less than number of terms, right? We counted before, we said our n was 3, there had to be 4 terms. Well, we can work backwards to figure out the n. I also know that whatever number is here, in other words, the a value, has to come out to this. And I know that because a to the 5 has to come out to 2, 4, 3, x to the 5. Because when I do the binomial theorem, it's always the coefficient is 1, then the number to the power of 5, and then the number to the power of 0. Well, this part always comes out to 1, so I don't have to worry about that. And this always comes out to 1, so I don't have to worry about that. So I know that this to the power of 5 has to come out to the 243. So let's think about that. How can I figure out what comes out to 243 to the x5? Well, the nice thing is we have a calculator button that helps us figure this out. On your calculator, if I want to figure out what the value is for a, I can take the 5th root of 243. If I do that on my calculator, I end up with 3. So I know the number is 3. I also know there has to be an x in here, because there has to be something in order to get this x5. Well, the only way that can happen is if it's an x1. Because 3x to the power of 5 comes out to that. And it's a little bit of problem solving. Let's try the same thing for the last term. I know the last term, b, has to be something to the power of 5 and come out to 32y5. Well, pretty obvious that this has to be the letter y. So the only thing I really need to think about is the fifth root of 32 is 2. So this has to be a 2. The only thing I've left for is a sign. Is it a positive sign or a minus sign? And I can tell that by looking at the signs in my question. The fact that these are alternating signs tells me this has to be a minus sign. Okay, so I did a little bit of guess and check there, a little bit of thinking. Yeah, I just had to problem solve, but I can do that pretty easily. So here's the questions I want you guys to try today. Just a couple, 3 of them. Okay, give them a try. It's just a small example of how we can use counting techniques in other areas of math. We like to put those in here from time to time so we understand what else I can do with this.